Good afternoon, everyone. Hope you all can hear me a bit away from the mic. It's pretty much audible, I suppose. So today I'm going to be talking about ViHy, which we call it as ViHy. It's an integration between the Virtuoso. It's a transient multi-phase simulator gas with the UWS research work on the gas harmony system. So they've been integrated together. So this is more of an extension talk to the talk which was already delivered in the previous symposium by my colleagues. That part of the talk was primarily to present the results about the matching between the experimental data conducted using Hydra Loop with the ViHy software. Now I'm going to extend the talk further beyond that because as in the last few months we've actually perform some more additional analysis to benchmark this ViHy tool, the real field operational case study. So let's get into this. Right. So a brief outline of what I'm going to be talking about today. The first 3 points pretty much are kind of a recap of what was already discussed in the previous symposium, very quick. And then I'm going to talk about the operational event case study itself, looking at a real field system. I will talk about some of the pros and cons or the uncertainties involved in predicting hydrate formation using the ViHy software, and also some discussion. Probably Bruce is going to chip in at that point to talk about some of the hydrate kinetic problems, as well as I will return back to conclude the discussion and also some future step forwards. Okay, briefly for some of you people who haven't heard about Virtuoso in the past, or maybe you were not present in the previous symposium. Virtuoso is a multi-phase transient flow simulator for hydrocarbons or even otherwise. Primarily, we deploy this as an online tool for production management systems, and it can be used as advisory. It has functionalities of advisory, and also it can be used for leak detection, restriction detections, or virtual metering. So, and also in addition to that, we can even do it as an engineering simulator where we can model anything from the sand phase all the way up to the oxide or even to refinery processing facilities and stuff. So in terms of, and then we have the UWA hydrate kinetic module, wherein the hydrate deposition rates or hydrate formation rates are predicted. So Virtuoso takes care of the transportation part of it, while UWA module will take care of the kinetics part of the hydrates. Now, so from between these two softwares, we have a bunch of parameters which are going back and forth between them for solving the issue or solving the system. So from Virtuoso, we tend to pass on typical properties like the dimensions of the system, as well as the operating conditions such as pressures, temperatures, liquid holdups, and also shear stresses and so on and so forth. And once it is taken by the UWA module then will predict the hydrate formation or the dissociation rates based on the operating conditions that are provided to it, and also the phase distribution of hydrate into each of the phases, and as well as the wall deposition rates. Now that's then fed back into Virtuoso, so it's a continuous cycle. It keeps iterating until the solution is found. So moving on, so in terms of the scope of modeling itself, I'll just quickly touch upon what is included as of the current version and what is not right now. So from a from an inclusions perspective, we can model the transient multiphase. Obviously, that's the Virtuoso part of it, and then hydrate kinetics, which is the UWA part, and then the hydrate transportation is taken care by Virtuoso, and the inhibitor tracking, as well as the effects on the equilibrium temperatures, saturations, and surface tension. Presently, the dispersal of gas in water and hydrate agglomeration and the cohesion, adhesion, and fracture, which some of it which Bruce has already touched upon, are not included yet, and also the non-Newtonian effects such as slurry flow, and also interfluid layer dispersal of hydrates. So it is a work in progress, and as the code gets developed further, that integration will happen as the time goes on. The Hydra model, I think this schematic on the left, probably most of you are aware of. You've seen multiple times. That's the Hydra Loop. Just very quickly, so the liquid and gas are pumped through or compressed and pumped through the loop, which is about 40 meters long, and the returns are taken into the separators, and the gas which is separated out of it feeds back into the loop. So it is a closed loop system, but since there are pressure and temperature values available all along the line, also at the inlet and outlet, we simplified this model in Virtuoso where we made it an open loop model. So essentially, it will allow us to remove all these equipments which are not necessary to be modeled, and the effects of pressure increase at the outlet can be actually taken care by time transient pressure as a boundary output variable, or as a boundary input variable. So that is still covered, but instead of having a full loop with all the equipment involved, we have simplified it to make it an open loop system. Quick comparison. This is just an overall summary of the Hydra data benchmarking that we've done. The left side two plots, the top one is the top one here represents the data from the experiment itself, and this one here is from the model. So if you look at the trend line, they are matching pretty well in comparison to the experimental data. And also when it comes to the parity plots, you can see that we are roughly in the order of about plus or minus 30% error margin. When we compare that, or when we consider the stochastic nature of hydrate nucleation and stuff like that, and the uncertainties involved in it, I think we are in a, I mean, this is a fairly decent agreement with the experimental data. So that's a very brief summary we have covered in until the last symposium, and this is the new work that we have embarked on. So we've looked at one of our implementation of Virtuoso, which is actually actively monitoring a gas condensate system. It's a fairly big network where there are multiple wellhead platforms, and you could see that like usually two wellhead platforms are actually connected into a single trunk line. There are about 4 trunk lines, and they are fairly long distance subsea, but in not so deep waters. So we have a Virtuoso implementation on this where it is doing, or it has been in operation since 1998, fairly long time, and we've been maintaining it for a fairly decent amount of all through this. And the functionality involved is it's a full-blown pipeline monitoring system. So all the operating conditions like pressure, liquid contents, temperatures, everything are always monitored actively. And apart from that, it also has a look-ahead forecast and what-if scenario functions are embedded into it, as well as peak planning tools and restriction or leak detections and alarms or any alerts are also included. So one of those pipelines has been taken for that study, for the study here, because there was an event at some point in time which happened, and it was believed to be a hydrate event. So we took the data for that particular pipeline, and we started applying the ViHy model so as to predict whether the hydrate formation event can be replicated in ViHy, and to what magnitude and to what accuracy. So it's a 36-inch line, fairly big diameter compared to what experimental setups are, 1 inch, 2 inches versus a full-blown 36-inch pipeline. It's primarily predominantly a gas production system with about 1 barrel per MMSE of water loading at the inlet, and about condensate loading of about 30 barrels per MMSE. So in a 36-inch line, what would that replicate? Hold up would be roughly in the order of about less than 5%. But because of the elevation profile, which the elevation profile, if you see this plot here, it goes up by about 70 meters as it goes towards the shore. and there are fairly quite a few valleys and dips and ups as it goes along the line. It's about 95 kilometers long. So there are going to be pockets of liquid holdup where those sharp valleys are there, and those will act as primary agglomeration points for hydrate particles and also maybe a blockage site. In terms of overall pressure drop for the flow rates that the pipeline is carrying, it is in the order of about 30 bar from inlet to the outlet, the overall pressure drop across the line. And in terms of the thermal performance of the system, the fluid temperature obviously starts higher at the inlet, and as it goes along, it starts cooling down. One of the interesting part is, since the fluctuation of temperature over the season can be quite big, there are situations where the ambient temperature is actually higher than the hydrate formation temperature itself. But because as the fluid traverses through the pipeline, which is predominantly gas because of the JT expansion, it's going to cool down as it goes along. And at some point, it's going to drop below the ambient and starts going into the hydrate region. So that is where you start forming hydrates. But then as soon as it hits the hydrate equilibrium temperature, it will start forming hydrates and releases some heat as well. So continuously, it's always hugging that hydrate equilibrium line, and all the time it keeps forming hydrates beyond that point. So this is the measured data versus the predicted data by Virtuoso from a pipeline directly taken from the PMS, or the pipeline management system, or production management system. So it is over a period of 60 days. The 0 day represents more of a transition between the seasons. So as it is entering into the winter season, and at about 53rd day or so, there was an event which showed that it was primarily because there was a drop in liquid rate. Sorry, or there was a drop in overall flow rate. So to say, the gas production has gone down, and then you see that the Virtuoso actually predicted a pressure drop, which was almost in the order of about 12 bar, but the real field system didn't predict that, or didn't show that pressure drop. So what happened there was the alarms were raised because there was an anomaly in terms of pressure. So it was perceived to be a hydrate event. So immediately the operator started injecting MEG, and because of the length of the line and at the rate at which you can inject, it took about 2 to 3 days for the MEG to reach to the point of interest, or the point of hydrate formation to be perceived, right? So at that point, once the MEG came into contact, you can see that after a couple of days, when the MEG is supposed to get in touch with that hydrate location, the pressure started coinciding again, which kind of suggests that it was actually a hydrate event, and because the MEG was able to get to the location of interest, or to the hydrates, it started dissociating it. And obviously again pressures started aligning together. So this was the event that we picked, and we wanted to use the ViHy tool to kind of predict if we are able to match the real field conditions. Right, so when we performed a baseline model, we looked at the overall hydrate volumes that in the entire system. So the hydrate volume started to increase from about day 20. That's when the temperature started getting lower, and it was hitting the hydrate temperatures. So the hydrate volume kept on increasing, and the green line actually represents the deposited volume onto the wall. So out of the amount of total hydrate, most of it is actually getting deposited, versus the suspended phase of the hydrates, which is going to get carried away along with the fluid, is fairly small. And this kind of gives us a conducive to conclusive evidence that it could form a blockage, and which could have been the reason for the pressure differential. Maybe it was not a full blockage, because obviously there was flow and we were able to still receive the production from the other side, but it was creating a fairly big restriction in order to do that. Because if you think about this, a slurry over the, I mean, let's say this entire volume of hydrates was only in the phase of a slurry. So even if it were to be a slurry increasing the viscosity of the fluid, it's not going to be enough to create such a big pressure drop. Unless it is a localized restriction, only then you will end up seeing such a big pressure drop. And when we look at the pressure trends, this is a zoomed in version between day 50 and day 60. So without the hydrates, the red line is fairly hugging until the point of the event itself, where it was not able to predict what the real field system was doing. And with the hydrate module on, consistently the pressure was above the real field data, which means because of the formation of hydrates all through the event, or even before the event also, there is higher pressure predicted, and that actually translates into during the event as well. That differential of pressure which dropped remains all through the experiment or all through the simulation. Again, when it comes back, or when the MEG was injected and it touches the hydrates and it starts dissociating, everything falls in line. Now, this kind of raised some questions for us, where we started thinking about, okay, what is causing this rapid development of pressure anomaly, given that, because usually the hydrates are not formed in such a big pipeline with such a low liquid content, it's not going to be formed immediately and it's not going to block off, right? So then we start thinking about what are the other parameters within the model which could start creating these anomalies. So the different factors that could actually impact the hydrate prediction or hydrate formation as well as the pressure drop predictions further would be, one would be hydrate wall adhesion or the adhesion forces, bathymetry discretization, as well as the supercooling or the probability of hydrate nucleation, and water loading, and also the entrainment as well as the particle size or the slip factors. So we started exploring each one of them as we went along. So first one, we looked at the bathymetry. So we looked at initially the model which was set up for the production management system in the Virtuoso, the online deployment tool, had a coarser profile, which is indicated by this solid black line. So as you could see, over 95 kilometers, this is fairly coarse. But then that was enough, or that was enough to get an accurate prediction to match the field data. So that was always being used, and it is still being used in the system with no mismatches. But then when it comes to hydrates, because of the localized water spots or the valleys where the water can actually accumulate, that becomes quite important. So then we rediscretize the pipeline with the finer profile as we got from the as-built data. So which then shows that there could be significant pockets of water that can be held up. But then there is another factor to this is, even though the water is being held up in these valleys here, it might not be necessary that the hydrate formation temperature has been hit at that point. So why you don't see anything further downstream, even though there are valleys, is because that water has been consumed to form the hydrates. Because downstream of about 50 or 56 kilometers, it enters into the hydrate region. So there is a difference in the amount of water hold up, and there is a difference in the amount of hydrate volume that can be formed because of this. So looking at the hydrate volumes, the coarser model actually starts forming hydrates earlier. Again, it's because of the way the water has been distributed in the system, depending on how the valleys have been put up. While the finer grid model is forming it a little later, as well as the volume doesn't start to go up until a little later than the coarser model. So, and also the hydrate dissociation part happens a little later in the finer model. That's because the MEG probably would have taken longer for it to travel along all the ups and dips to get in contact with the hydrates. And it is quite apparent even in the pressure trends. So both the profiles or both the trends actually match together with that differential that was always there. But then after the event or even after the MEG comes in contact, the trends do not match with the field data, especially the one with the finer model, because there is more water being held up. So there is more pressure drop. It's not really because of the hydrates itself, it is primarily because of the extra water that is being held up. So all of this will tell us that the discretization of the model is quite important to be able to kind of look at closely where the water pockets are and where those hydrate blockage sites could be. And next up was we looked at entrainment. So instead of using the baseline entrainment as per Panhard equation or Panhard model, we also tried to bump it up by another 50% to kind of see whether it will have an impact on overall pressure trend. It does have an impact, but it only produces an extra volume of about 20%, which is not sufficient enough to create any difference in terms of the pressure trend. So at this point, entrainment was not such a big factor for us to play around with to be able to match the field data. So then we moved on to the next one, which is adhesion forces. So initially we started off using the previous version of the UWA code, where the adhesion forces were not sufficient enough to push the hydrates to deposit at a certain location. So what was happening was, if you look at this plot here, all the hydrates that were being formed were actually being maintained in the slurry phase or within the suspension, and they are being carried away through to the flow line, and it was just being flushed out of the flow line. So there was absolutely no deposit being formed, which is indicated by this green line at the bottom here, which is using the older version of the DLL. Then upon close communication with UWA, we kind of figured that probably the adhesion forces may need to be revised a little bit. So once those forces have been revised, now we start seeing a lot more holdup of hydrate depositing on the wall, which is the yellow line. Pretty much most of the hydrate that is formed is actually being deposited onto the wall, and only a little remains in the suspension. That also is corroborating pretty well with the pressure trends. So with the old DLL, although it was lower, but then as we increase the adhesion forces, because there is more deposition being formed, it is continuously predicting a higher inlet pressure all the way through, not only just at the event duration, but also all across. So there is a difference in terms of the pressures during the events, and there is an excess DP that is predicted. So again, adhesion is one of the key parameters that we need to look at, and it is one of the uncertainty that remains. Next one was about the water loading. So this particular system was supposed to be 1 barrel per MMSCF of water loading as it comes into the inlet, or the production comes into the inlet. But it is not recorded on a continuous basis. So there have been indications that it could go up to as much as 3 barrel per MMSCF. So we went ahead and did some additional sensitivity with increased water loading. And so the water loading was increased at somewhere at the midpoint of the simulation, which is at about halfway through at about 30th day. And as soon as we increase that, obviously more water is coming through, and also more hydrate is being formed. So when we compare that against the field data for inlet pressures, obviously there is a big jump in the overall pressure trend, which continues to exist all the way through the simulation. That is primarily because of only water loading. It's nothing, I mean, although there is more hydrate, but it's primarily because of the additional water that is being loaded. So I think most of the systems, again, may or may not continuously track the water loading. So we need to be cognizant of the fact that there could be variances in the production that is coming into the system. So the predictions can be off. Now, I would like to touch upon a little bit on the stochastic nature of the hydrate nucleation itself. So this is actually this was a paper or the work from a paper which was done by one of my colleagues, Human Hagigi, as well as I think Professor Tohidi is also online, I suppose. So this is probably, I mean, the same plot might not be there. It is a bit modified version, but just to give you a sense of the stochastic nature I'm talking about. So typically when a system is shut down or when a system is cooling down, your pressure starts falling down. And when it gets to a point where it starts touching the hydrate equilibrium curve, your hydrates are forming and the pressure drops very rapidly. So you're looking at two different slopes, and this inflection point could be probably termed as the nucleation point. But if you were to do this experiment multiple different ways with different starting conditions and a different set of parameters, that curve can, or that inflection point could be different. So it's not always repeatable. So that's where the stochastic nature comes in. Your hydrate nucleation may not be exactly true or exactly predictable in that sense. But dissociation is on the other side much warmer compared to the formation side. So typically for gas condensate systems, it could be in the order of about 3 or 4 degrees centigrade when the hydrate form versus the hydrate dissociation. Although you are in the hydrate zone also, you might still need additional subcooling or supercooling. So that's what we are talking about. I mean, that's what we are terming it as supercooling within the hydrate zone to be able to actually form hydrates. So so there is always going to be a hysteresis effect there in that sense. So we started looking at the supercooling part of it. So instead of forming the hydrates right up against the hydrate curve, we looked at whether if we push the hydrate formation temperature by about 3.6 degrees into the hydrate zone. So we don't allow although it may cross the hydrate formation curve, we don't allow the hydrates to form until it hits 3.6 degrees of subcooling below the hydrate formation. So it is interesting to see that the hydrate formation, which is represented by the red line for the supercooled version of it, is dramatically reduces. Whereas if we were to shift the hydrate curve, even with that supercooling, if we were to shift the hydrate curve to the right by about just 1 degree, it would be a dramatic increase in terms of hydrate formation. Now, obviously, because you're going to be forming hydrates earlier, and that kind of represents more amount of hydrate that can form, and which again follows the trends as expected for the inlet pressures as well. So the purple line, which is with that 1 degree shift of hydrate, is having the highest inlet pressure, and also the magnitude of drop doesn't change in any one of these simulations. So yeah, then moving on. So with all these discussion that we had till now, where I talked about the uncertainties and the stochastic nature of the hydrate nucleation. So the way we look at this one is, so depending on all these different parameters that are uncertain, we think that a practical application for hydrate modeling would require a probabilistic tool rather than a deterministic tool, right? It's more like a good analogy here would be like a hurricane path determination, right? So if you were to apply, let's say, a Lagrangian model to determine the paths of a hurricane, you will come up with n number of solutions. I mean, but then it's more about the probability of which one is the most severe or which one is the most probable to happen. That's what would be reported. So the difference would be, you might be, I mean, one probability versus the other, you might be hitting a fully populated zone versus just the storm might just fly through a desert, right? So that's the kind of nature that we are looking at even for hydrate prediction, more of a probabilistic nature rather than a deterministic nature. Now, the target prediction with that kind of a probability would be the likelihood of hydrates, likelihood of blockages, and also we can estimate the scale of hydrate formation, as well as we can estimate the time during which it might form or the time for remediation. But the exact location is something that may not be precisely predicted. And I think we have seen that in many different models, exact location of hydrate formation cannot be predicted that precisely. And also the precise time at which it will form is another thing which we may not be able to, apart from others as well. So in order to kind of get, I mean, to further corroborate the feasibility of using it as a probabilistic tool, we went ahead and performed an ensemble of simulations, about 7 different simulations, which all were performed for a duration of 24 hours and were done one by one, only varying one parameter at a time and with the same initial conditions to start with. So what we varied here was a range of supercooling, 1 degree, 2 degree and 3 degrees, and also 1 degree shift of the hydrate curve itself versus 1.5 times, which is 50% increase of entrainment, as well as the slip factor was also varied. Now in all of these, what we can see is there is a fair bit of scatter of where the hydrates form, as well as the volume of hydrates that are formed. So it is in the order of about 40% for peak hydrate location, and about 50% for peak hydrate holdup. But then the hydrate volumes in itself were fairly good in the prediction, and they kind of follow the trend that we expected to. And although it is not presented here, the inlet pressures in all these conditions were in fairly good match. So all of this will again corroborate the fact that it must be more of a probabilistic nature tool rather than a deterministic tool. So now here I would hand over to Bruce to talk about some of the developments on the
Ready? Thank you for that, Leap. So as Leap has mentioned, probability, very, very important, and we'll be hearing a full presentation from Mark on that a bit later on. In the meantime, I just wanted to quickly go through some of the updates to the actual underlying mechanics of the model. So I spoke a little bit about that at the end of my presentation, but I guess in addition to that, and I guess of particular relevance to both these natural hydrate production and also for any low points where you have a substantial amount of water, is the idea of what happens in bubble flow. So this goes back to the work that we saw previously that Shinsuke had been doing, in that if you have these bubble flowing systems and you have conversion of each of these individual bubbles within that system, you have to have some idea of what effect that's going to have on the slurry viscosity. Now, this isn't something which is currently taken into account, but we have done, as you can see here, a whole range of work on working out exactly what that viscosity looks like. So this is actually quite different to what we would see in oil-dominant systems, and what we are looking at the moment is implementing these specific mechanics. Now, I guess one of the key points here is that from the visual observations that we've had in the HAL flow loop down at Oil-Filled Technologies, we've actually been able to characterize not just viscosity increases as a function of the amount of hydrate in there, but what's the actual effect on our flow. So can we see blockages occurring? Can we see restart and these sorts of things? So what we actually wind up finding is that for these bubbly type systems, you tend to form networks of hydrates, which can cause jamming at reasonably low volume fractions. And our idea here is that essentially you may have these deposits forming. Again, that's a very important point. And then as you have numerous converted bubbles and hydrate particles coming into these stagnant zones, you can very rapidly wind up with these jamming or sloughing or all of these different phenomena which can suddenly and probabilistically lead to rapid blockages of the sort that we see in the very sudden change in pressure drop data, for example. So this is really going to be key to bringing in the ability to model these sorts of phenomena. Now, if we talk just quickly about how we might go about incorporating deposit movement into these simulations, this is again another figure from one of Shinsuke's papers, which is currently under review, looking at, for that water dominant system, what is the critical shear stress required to begin moving a deposit which exists within a pipeline, right? So you can see, as you would expect, as you get more and more hydrate, it becomes more and more difficult to actually start moving that deposit and restarting the entire pipeline. And we looked at a range of different things. For example, the nature of the restart. So do you ramp things up very quickly? Do you linearly increase that pressure drop ramp across it? And I'm hopeful that you'll be able to read about that in the paper, which is coming out shortly. But I guess, relating these water dominant systems to our gas dominant systems, we can kind of think about that ability to restart as being integrally related to our ability to move deposits within the gas dominant model, for example. So we saw, again, in the last in my presentation, this figure here looking at the shear stress which exists on a deposit before or as predicted by our models. So what we can start to do is to take information from the experimental apparatus. We can compare it also with what it is that our models are putting out in terms of that shear, and also with other fundamental experiments done on the actual strength of these hydrate deposits to get some idea of when our sloughing might actually occur. Now, that's only sort of half the story, is the ability to do that within our extension. The other half is the ability of the multi-phase tool that we talk to actually support that. And that's been a real joy, to be honest, working with the folks at Wood, in that they've been very responsive to the needs of putting in these new mechanics. So if we find something which isn't perhaps modeled in the way that we would like it, then we can talk to the guys at Wood, and they're very happy to look at incorporating this within the simulation tool. So that sort of relationship of working out what are the new mechanics from the hydrates perspective, and then what are the requirements within the flow tool, is something which has been very useful and will be very useful in the future in continuing to develop ViHy. So I just wanted to bring those 2 points up, and now we'll have a look at the conclusions.
Thanks, Bruce. Thanks for that summary up there. In conclusion, I would like to say that from the first phase of the study, we were able to achieve a stable, numerically good simulator, which is tightly integrated with Virtuoso and UWA, Hydrate Kinetics model, which is able to predict all the leading order physical phenomena that we expect, which is multi-phase transport, thermal effects, wall deposition, and effects of inhibition in a fairly good sense, and with good validation and testing that has been done against the experimental data. Now, in terms of the real field applications, I've already touched upon many of the uncertainties and the stochastic nature of the hydrate nucleation itself. So, in essence, what we are looking at is this last point here. Results so far suggest that the probabilistic tool is an appropriate goal for industrial application. Going forward, what we are looking to do is we want to do a further detailed modeling of gas dispersion in liquid, slips, as well as water dispersal in oil, and from the Hydra data also looking at the correlation timing as well as location of sloughing or the slurry effects that probably will be incorporated in a future time. And that brings to the end of the talk. I'm happy to take any questions.